Good day, bright physics students. So for today's video, we will try to understand the concepts behind momentum and impulse. And we are still under chapter number 7 of our series of video lessons for general physics. Alright, so without further ado, let's begin. In order to understand better the concepts of momentum and impulse, we should start by defining it or by giving a definition that will suit translational motion. Alright, as you may remember from our previous lessons, there are 3 types of motion in general physics. Number 1 is translational motion, number 2 is rotational motion, and number 3 is vibrational motion. Alright, so again, in order to understand better the concepts of momentum and impulse, we should start from the very basic, and that is through translational motion. Okay, and the version of momentum for translational motion is called the linear momentum. And according to Sir Isaac Newton, he described linear momentum as the quantity of motion. So, a little trivia before we proceed in the next slide. Actually, Sir Isaac Newton doesn't define his second law of motion by the acceleration of the object, but rather by the use of the concept of momentum. And we will try to elaborate that in the next slide. So again, the definition given to us by Isaac Newton for linear momentum is the quantity of motion. Alright, so what really is the linear or the description that we had for linear momentum? So according to this slide, linear momentum of a particle or an object that can be modeled as a particle of mass m moving with a velocity v is defined to be the product of the mass and velocity of the particle. So to better understand the description that was written in the slide, you can actually cut the sentence from here up to here. So the linear momentum is defined to be the product of the mass and velocity of the particle. So before we do anything else, let's try to give, or let's give first the symbol that we use for linear momentum. And that symbol is a small letter P with an arrowhead, which means that linear momentum is a vector quantity. Alright, so let's write it. Let's write it there. So again, linear momentum is a vector quantity, which definitely meant that momentum requires direction. Right? Not just the magnitude of the quantity, but also the direction of motion itself. Alright, so according to the description, it is defined to be the product of mass and velocity of the particle. So if we took that literally, the mathematical interpretation of this description would be P, vector P, is equal to the product of mass, which has a symbol m, and velocity, which has a symbol v with an arrowhead. Alright, so if this is the formula that we had for linear momentum, as you may see from the quantities that was present in our equation, it basically used the concept of mass and velocity, and this is the reason why Isaac Newton described his second law of motion using momentum rather than acceleration, because it will be easier for people in his time to describe the motion of the object by identifying its mass and its velocity, because it is the speed of the particle of interest for that particular matter. Alright, now unlike acceleration is actually a derivative of velocity with respect to time. Right? That's why it's defined as the change in velocity over a certain period of time. Alright, now aside from this, aside from linear momentum, which uses the product of mass and velocity to gather its own magnitude and direction, another physical quantity in physics also uses mass and velocity in its formula. Alright, and it's written just like in this format. So we have 1/2 mv squared, and we knew that this equation is for the kinetic energy of the object. So just like linear momentum, we also use mass and the magnitude of velocity for kinetic energy. However, the difference, or the main difference between these two physical quantities, is that kinetic energy, alright, kinetic energy is a scalar quantity, which means that it doesn't require or it doesn't need the direction of the object itself, whether it's moving to the right or to the left. As long as we calculated and knew the magnitude of energy, then we're already done with our computation. However, as for linear momentum, we need to get the direction of the motion of the object. So let's say, for instance, we have a particle that moves 5 meters per second to the right. So if we're asked what is the direction of the linear momentum of that specific particle, then the direction will copy the direction of the speed or the velocity of the object. So if it was mentioned earlier that the particle moves to the right, then therefore the linear momentum of the object is also pointed to the right, as compared to the kinetic energy of that object. The only thing that we actually need in our scenario earlier would be the magnitude of the velocity. Okay? And we don't, or we omit the directionality of the velocity again. Alright? So yeah, this would be the description that we will be having, or we will be using for linear momentum. Alright, so let's have some applications of linear momentum in the real setting. So let's say we had a truck, okay, with a very small velocity, or maybe perhaps a bigger boat, alright, with great mass, but is moving at a very low velocity in terms of magnitude. So it still has greater momentum because of its mass. And there are also examples of tiny objects, alright, that has the least mass but is moving at greater velocities, just like a bullet, right? Just like a bullet that is fired from a gun, right? The velocity of that bullet would be great in magnitude, so that bullet will still have a massive magnitude of linear momentum. Alright, so those are some examples of linear momentum in a real world. Alright, now let us try to consider what happens when these two cars collide. So earlier we defined linear momentum as if we had a particle, a single particle in space that moves at a certain velocity. Right? That's why we use that formula, mass multiplied to velocities, or the velocity of that particle. However, what if we have two different particles inside a system, just like what happens in this GIF? We had two cars, and these two cars are colliding with each other. So in this particular GIF, we know by observation that the masses of these cars are equal in magnitude, because they are the same model, right? And probably they are moving at the same velocity, but in opposite direction. That's why at the midpoint of these GIF, they collided. All right. Now, there are two possible ways that we can actually interpret what happens within this GIF. Alright, so we can interpret that using Newton's third law and Newton's second law. So we can identify what or what is the distribution of the forces inside that system. Alright, so as you may see, the red car is applying a force towards the yellow car, and the yellow car is also applying a force towards the red car. That is why, as they collided, apparently, because the GIF is not, it's not complete, in the sense that it doesn't show what happens after the collision of these two cars. Alright, so anyway, if we try to look at the distribution of forces within that kind of system, we can conclude that the force exerted by the red car towards the yellow car is the same force that was exerted by the yellow car towards the red car. And that is how we interpret that scenario using Newton's third law. Right? The magnitude of the forces experienced by each car is the same, and mathematically we can write that just like this one. So the force experienced by object number 1, that is the red car, towards object number 2 is equal in magnitude of the force exerted by the object number 2, which is the yellow car, towards the red car, but opposite in direction. That's why we included that negative sign right there. Alright, now, how can we interpret what happens inside that system using this Newton's second law? We know that Newton's second law is like trying to define what happens to the acceleration of a particle, knowing that it is affected by a certain force and the particle has its own mass. So if we can summarize the Newton's second law, it is written in this equation. So the acceleration of the object is directly proportional to the force exerted on it, and inversely proportional to the mass of that particle. Alright, so based on what we knew about Newton's third law, if the forces exerted by two particles inside that system, which is in this case the cars, are equal in magnitude and opposite in direction, so we can exclude the magnitude of force in here to identify what happened to the acceleration of the cars after collision, because it wasn't literally shown in the GIF right here. Alright, so another quantity that could affect the motion of the object after collision would be the mass of the object. That is why that would be our interpretation of the GIF using the second law of motion. So the result of those forces on the motion of the car depends on the mass of the car. So let's say, for instance, instead of colliding with the yellow car, the red car collides with a truck, a 16-wheeler truck. So even though I won't show it in this slide, we can visualize what happens in what will happen in that kind of situation. Maybe the truck will eventually drag the red car towards the direction of its own motion, or perhaps it would crash the car on the spot. Alright, so those are the possible scenarios, but again, we can conclude that the mass of the particle colliding with another particle could possibly affect the motion of that particle or of the other particle. Alright, now these two concepts that we describe right here would be relevant for us to understand the second conservation law in physics. So by the way, as a little review, the first conservation law that we described in our video lesson, it would be the conservation of, alright, let me just write it in here, conservation of mechanical energy, and that is discussed in the previous chapter. And the second one would be conservation of momentum. Alright, so in order to understand and grasp the concept of conservation of momentum, these two concepts that we recently discussed, which is the Newton's third law and the Newton's second law, would be relevant in order for us to understand what really transpired with the conservation of momentum. Alright, so let me just show you this problem. Let us consider the situation. So let me just read the problem. According to the problem, we had a 60 kilogram archer that initially stands at rest, and then the archer is currently or is initially probably lifting an arrow which has a mass of 0.03 kilograms. Remember that they are on a frictionless ice for that specific scenario. Now, as the archer fired the arrow now eventually gains a speed, and that speed has a magnitude of 85 meters per second. So now, if we can still remember what we've discussed in the previous slide, in a system of two particles or of two objects, when one object applied a force towards the other particle or other object, the other object would definitely apply a force that is opposite in direction but equal in magnitude of the force applied by the first object. Right? So, since we already had discussed force diagrams and energy models, can we actually solve this problem using those things? So using force diagrams, so if you can remember that is also the free body diagram. So if we try to use force diagrams, we can't actually solve this problem because we don't have any information about the acceleration of the archer. As for energy models, we can't also use that because we don't have the work done in pulling the bow, right? And we will definitely need that in order to solve for the missing quantity, and that is the velocity of the archer. All right, since we can't use those models and diagrams that we've discussed in the past. That's why we also definitely need to understand the concept of momentum, because only momentum could answer these types of problem, which again involves mass and velocity of two particles. Alright, now in order to better understand what is the concept of linear momentum, so let's try to imagine this. Let's say for instance we have two different particles. One is a blue particle and the other is a red particle. Alright, so let's name the blue particle as m sub 1, because definitely it has a mass, and the red particle as m sub 2. Now, these two particles are located in an isolated system. So let me just write it in here. And if you can still remember, an isolated system, in our discussion of energy and energy conservation, when particles are located in an isolated system, in terms of energy, the total energy, right, the total energy of the system is constant. That is why if we try to look for the change in the energy of the system, it would be equal to 0, because that is the equivalent or the equivalent magnitude of the word constant in when we're trying to look for the change in that quantity. Alright, now, so of course, if also we're trying to know the magnitude of the net force or the total force, the change in the net force inside the system, that would also be equal to 0, because again it is isolated. So therefore there are no external forces acting inside our system. So basically what we're trying to say in this type of system is that the only thing that we will consider is all the forces within the system at within our current observation, and as well as the mass of the masses inside the system. Right, so we can't add another particle within our scenario, while trying to like understand what happens within the momentum of the system. So yeah, so basically we're just trying to eliminate all the other factors that could affect the momentum of the system. All right, now, so since we already had the system and established that these two particles are located in an isolated system, so let's say that these particles are moving at a certain velocity. So let's name these vectors as velocity of each particle. So this one is the velocity vector of particle number 1, and this one would be the velocity of particle number 2. Alright, since these particles has their own masses, if we can still remember our discussion of types of forces, alright, this is a field force because there is no apparent contact within these particles. What type of field force is present within these two, knowing that they had their own masses? Okay, so if there is a presence of mass, then therefore the force experienced of by these two particles would be the force of attraction we call now as the force of gravity. Alright, so we have here these two arrows will represent now the force of attraction that is experienced by the two particles. Again, that's the force of gravity in that context. Alright, so let's name this vector arrow as the force directed towards particle 2 experienced by particle 1, and this force is the force directed towards particle 1 experienced by particle 2. Alright, so now if you try to look at it in the diagram that we had in here, the two vectors are equal in magnitude but opposite in direction. So if we again write it down using our equation from Newton's third law, that would be F21 is equal to negative F12. Alright, so mathematically we can rewrite this equation by using this formula. So this will be F21, and then we transpose F12 inside our equation, so plus F12 is equal to 0. And this equation actually proves our assumption earlier in the in our discussion, which is the change in the net force inside the system will be equal to 0. Alright, now let us try to use Newton's second law. So let's use Newton's second law to get the equivalent values of these forces. Alright, so according to Newton's second law, force is equal to the product of mass and acceleration. Alright, so F21 is the force experienced by object 1, right? So that would be m sub 1 times a sub 1, right? Plus, so F12 is the force experienced by object number 2, so that's m sub 2 times a sub 2 is equal to 0. Now we know that acceleration is related to velocity using kinematics. So let's use kinematics in order to get the velocity with respect to time function or derivative, because again we know that acceleration is related to velocity in that kind of situation. Alright, so using kinematics, we know that acceleration is equal to dv over dt. So derivative of velocity with respect to time. So our equation will become like this. So m sub 1 times dv1 over dt plus m sub 2 dv2 over dt is equal to 0. Alright, now since mass or the mass of these particles are constant, it is a constant property of matter, so we can include that within our derivative. So our derivative would look like this. So dm1 v1 over dt plus dm2 v2 over dt is equal to 0. Alright, so let's try to look at this. Since they are the same. So dmv over dt, let's write it in here, dmv over dt is similar with dp over dt. Alright. They are equal because we know from our from the previous slides that the product of mass and velocity is equal to the momentum of a particle. So that is equal to dp over dt, and we know that dm1 v1 over dt is equal to the force of the object, or the force experienced by the object. Alright, so we already had one equation. Alright, so this is the relationship of momentum with force. So force is equal to the derivative of momentum with respect to time. Aside from that, okay, we can go back to this equation and factor out d over dt. Okay, d over dt multiplied to m sub 1 v sub 1 plus m sub 2 v sub 2 is equal to 0. Alright, and this equation would be very much needed within our discussion of conservation of momentum. Alright, so again, if we try to get the sum of the product of momentum, mass rather, and velocity of a particle with respect to time, that would be equal to 0. And this only happen when the particles are located in an isolated system. Alright, so what do we learn from these derivation? So what we do learn is that linear momentum is defined as the product of mass and velocity, and we proved that using the derivation earlier. And the SI unit that we had for linear momentum would be kilogram meter per second. Kilogram is the unit of mass, and meter per second is the unit of velocity. That is why we arrived in this unit. Aside from that, you can also use Newton second as a unit for linear momentum. Alright, so aside from this, we also can use that derivation to analyze isolated systems and what happens to the momentum of the particles present in an isolated system. Right? So first thing that we can actually get from that is that the total momentum inside an isolated system is also constant. And from our previous discussion, we established that whenever we see the word constant defining a totality of the magnitude of a certain quantity inside the system, if we try to look for the change for that specific quantity, so change in the total momentum would be equal to 0, right? Because this is the equivalent value or magnitude of that word. Alright, now so if we can remember mathematically, delta, or that triangle right there, symbolizes in mathematics a change. So that is final momentum minus initial momentum. Or we can rewrite that equation like this. Alright, so in the left side you can locate the initial momentums of the particles within that system, and in the right side you can locate the final momentum of the particles within that specific system. So we can summarize this equation as this is the before collision. So this is the momentum of the particles before collision, and this is the momentum of the particles after collision. Alright, so let's say for instance we have two different particles. So this particle right here and this another particle. So let's say that this is m sub 2 and this is m sub 1. M sub 1 is 1 kilogram and m sub 2 is 2 kilograms. The velocity of m sub 1 towards m sub 2 is equal to let's say 5 meters per second, and the velocity of m sub 2 towards m sub 1 is also 5 meters per second. So they had the same magnitudes of velocities but different in direction. Alright, so if we're trying to compute for the initial momentums of each particles. So the initial momentum of object number 1 is obviously 5 kilogram meter per second, and the initial momentum of object number 2 is equal to 10 kilogram meter per second. Alright, so if we try to get the sum of these two, so we will get a magnitude, or we will obtain a magnitude of 15 kilogram meters per second, which is the momentum of the system before collision. According to our analysis model, the initial momentum of the system should be equal to the final momentum of the system. So if that is 15 kilogram meter per second, then therefore the final momentum of the system should be equal to 15 kilogram meters per second. Alright, and this equation, so whenever there are two or more particles in an isolated system that interacts, the total momentum of the system does not change, and this statement is the conservation of momentum. Alright, so now at least we had established the idea of linear momentum and what happens to momentum of the particles within an isolated system. So it is conserved. Right? So if the particles are located in an isolated system, conservation of momentum takes place. Alright, so another description that we need to remember for conservation of momentum to happen, aside from the particles located in an isolated system, the particles could also be located inside a closed system, wherein there are no mass or no particles or no objects should enter or leave the system. Alright, so yeah, let's try to apply our learnings into sample problem number 4. So according to sample problem number 4, this is our problem earlier, the problem with the archer. So we had the mass of the archer and the mass of the arrow. So let's label the mass of the archer as m sub 1. That is 60 kilograms. And the mass of the arrow, m sub 2, is equal to 0.03 kilograms. And the velocity of the arrow after firing. So since it's the velocity of the arrow after firing, so this would be the final velocity of the arrow. So v2f is equal to 85 meters per second. So why is it the final velocity of the arrow? So what is the initial velocities of the archer and the arrow? So the initial velocity lies within this statement. So since both the archer and the arrow are initially at rest because they stand in that frictionless ice, so we can conclude, or we can assume, that the initial velocity of the archer is equal to 0 meter per second, as well as the initial velocity of the arrow. That is also 0 meter per second. Alright, now how do we solve this? Because it is mentioned in the problem that the archer stands in a frictionless, or on a frictionless ice, so there are no external forces acting within our system. So basically, if there are no external forces, it is within an isolated system, and we know that in an isolated system the change in momentum is equal to 0, and that symbol right there, the delta symbol, mathematically that is final momentum minus initial momentum is equal to 0. So we can transpose initial momentum to the other side. So it will give us this equation. So final momentum is equal to initial momentum. And we know that the initial momentum of the system is equal to 0 because the initial velocities of both particles located within our system is also 0. Alright, so the final momentum would be would be equal to this formula. So that would be m sub 1 v sub 1 f plus m sub 2 v sub 2 f is equal to 0. Again, because the initial momentum is equal to 0. Now we need the final velocity of object number 1, and that is the archer. So transpose m2 v2f to the other side. So this will become m1 v1f is equal to negative m2 v2f. Alright, and then we divide both sides by v1f. Okay, so cancel this one. Sorry. Oh, sorry, my mistake. We should divide both sides by mass, not by initial velocity. Sorry. Alright, let's just erase that. Alright, so let me just state again the what we will do inside our equation or inside our solution. So we divide both sides not by v1f or the final velocity of the archer, but by the mass of the archer, because that is the given and the unknown is the final velocity of the archer. So our formula would be v1f is equal to negative m2 v2f divided by m sub 1. So then we substitute all of our given. So m sub 2 is the mass of the arrow, so that's 0.03 kilograms, multiplied to v2f. v2f is 85 meters per second, divided by m sub 1, that is 60 kilograms. Alright, so v1f is equal to, so we can cancel the unit kilogram, so our answer for this question is negative 0.0425 meters per second. Alright, and that is our final answer for this question. So is it okay that we have here a negative sign in our final answer? So that is fine, because this is a vector quantity, so which means that the negative sign in our final answer indicates the direction of motion of the archer. So this is on the assumption that the archer and the arrow is initially located at the origin of our coordinate system. So as the archer fired the arrow, so it moves to the right of the Cartesian plane, and since the force applied by the arrow towards the archer is to the left, then the motion of the archer is also to the left. That explains the negative sign of our velocity. Alright, so I hope that you understand sample problem number 4. Again, if you don't, you can easily press the time stamps that I have included in the description box. Alright, so let's proceed. How about if the particles are located in a non-isolated system? So if the particles are located in a non-isolated system, this time we will use the relationship that we already established or derived in the previous slide of force and momentum. Alright, so we will use this relationship in order to identify what happens with momentum once the object or the particles under investigation is located in a non-isolated system. So according to our derivation earlier, the force is equal to the derivative of momentum with respect to time. Now, since we wanted to know what happened with the momentum of the object, so we multiply both sides by dt. Alright, so yeah, we can cancel this one. So now we're left with f dt is equal to dp. Alright, now since we wanted to know what type of physical quantity is produced when we are identifying the change in the momentum of the object, so we integrate the equation. So if we integrate the left side of the equation, we would also integrate the right side of the equation. Alright, so let's use the right side of the equation first. So if we integrate dp, so this is simply equal to momentum. Alright, so this is simply equal to the momentum of the object. However, if we establish a limit within our integral, so if our limit is the initial state of the objects or the particles, and the final state of the objects are our upper limit, so it would be change in momentum. Alright, so change in momentum, that is again equal to PF, final momentum, minus initial momentum. So again, that's delta P. And this quantity, so whenever there is a change, alright, this is change in momentum. So remember, whenever there is a change happening within the magnitude of our momentum, whether it increases or decreases within our non-isolated system, it wasn't simply defined as momentum, right? It is the impulse of the object, which has the symbol J with an arrowhead, because it is also a vector quantity. Alright, so this symbol right here is what we call now as impulse. Alright, so let's rewrite our equation on this side. So that's J, impulse, is equal to change in momentum. This is our first equation. Right, this is the first equation that we derived using the force and momentum relationship. Right. Aside from that, we know that the change in momentum, which is again equal to the impulse of the system, is equal to the integral of the derivative, or the integral of dp, and integral of dp is equal to the integral of f dt. So that makes impulse also equal to the integral of f dt. So this second equation is the general formula. This is the general formula for the impulse of a system. That is the general formula. Now, what if we had a certain condition wherein inside the system the force or the magnitude of the force is constant? So let's write it in here. So for constant magnitude of forces, so again, in mathematics, if we try to integrate a function and there is a constant within that function, we immediately exclude that and take that away from our integral, or outside our integral. So that will become J is equal to F integral of dt. And integral of dt is just like this one. So as we integrate dp, we obtain delta p. So what will be obtaining from this equation? Impulse is equal to F delta t. Right? And this equation only happens when, again, the force within our system is constant. Alright. So now, what do we learn about this analysis model of the momentum of particles within a non-isolated system? We obtained a new theorem. So the new theorem that we obtain is the impulse momentum theorem. According to the statement, it is the change in the momentum of a particle, that's delta p, is equal to the impulse of the net force acting on the particle. So that's J. Alright. There are lots of great application of impulse. And actually, the idea of impulse saved a lot of lives. Because, you know, when car companies before design their cars, they usually use materials that are so rigid, right? That when that car or a car collides with a wall or another car, the car remains stable, all right, but the driver would possibly be dead, because the driver immediately receives the force that was bluntly received by the car initially after the crash. But in our era, the car manufacturers made sure that the materials that they use for their car would eventually receive the force first. That is why you you would see dents in the car whenever it whenever there are the driver collides with a surface, perhaps, or the design of the car includes airbags. And the airbags, so according to the formula that we had for impulse, if the force is constant, or the force received by the car is constant, the airbag would increase the time. Alright, so in our formula for impulse is equal to F delta T. So if the car experienced a constant force due to the crash, so the airbag would increase the time in order to increase the impulse. And as we know, impulse is the change in momentum. So it would decrease the momentum of the car, or the force that would eventually be experienced by the driver would be less in magnitude. That is why there are lots of drivers, even though they recently like collided with a surface or a wall or another car, they're still alive because of that. Right? There are also other applications for impulse in sports. Actually, there are lots of application of impulse, like the wearing of a helmet, gloves in boxing, or baseball gloves in baseball, wearing knee pads. So those clothings, those things that the athletes wear actually increases the time of the impact, or the force, so that the force would be less in magnitude when the player actually received it. Right, so that is the takeaway that we have for non-isolated system. Alright, so as a recall and as a summary, if a particle or the particles are located within an isolated system, momentum is conserved. And if the particles are located within a non-isolated system, then there is a change in momentum that happens within that system. Therefore, impulse is produced. That's why we produce the impulse momentum theorem. Alright, so again, these are the examples that I have mentioned earlier. So alright, so let's try to solve sample problem number 5 in order to apply what we do learn from the previous discussion. So according to the problem, in a particular crash test, a car of mass 1,500 kilograms collides with a wall. The initial and final velocities of the car are negative 15 meters per second. That's the initial velocity of the car, because the direction of the car initially is to the left, towards the wall. And the final velocity is 2.6 meters per second. That is positive because after collision, the car would move backwards. So that's to the right, respectively. If the collision lasts 0.15 seconds, find the impulse caused by the collision and the average net force exerted on the car. So let's write all of the given that we had in that problem. So the mass of the car is 1,500 kilograms. The initial velocity of the car is negative 15 meters per second. The final velocity of the car is equal to 2.60 meters per second, and the time for that the collision happened actually is 0.15 seconds. Alright, now since obviously there is the problem looks for number 1, the impulse, and that's the first thing that we need to look for, and number 2 is the net force. So this is a work under non-isolated system. So we need to use all of the things that we learned in a non-isolated system. So again, if we try to look out for momentum in a non-isolated system, it is changing. Therefore, we use the formula of impulse. So impulse, as mentioned earlier, is the change in momentum, and that is equal to final momentum minus initial momentum. Now, final momentum is equal to mass times final velocity minus mass times initial velocity. Since the masses in our equation are equal in magnitude, so we can factor that one out. So that's m times final velocity minus initial velocity. So we can now substitute our given inside our equation. So this will become mass is 1,500 kilograms. Final velocity is 2.6 meters per second minus negative 15 meters per second. Alright, so the impulse is equal to 26,400. So the unit is the same as the unit of momentum, that is kilogram meters per second. So why is it the same unit with momentum? Because remember, the only thing that changes the only thing that actually changes in our formula is the magnitude of the total momentum inside the system, and not the quantity. Alright, so that is still kilogram meters per second. Now, the second thing that the problem wanted us to look for is the magnitude of the net force. So if we're trying to look for the magnitude of the net force, then we can assume that it is a constant force because it's a net force. Alright, so using the formula that we had earlier, J is equal to F delta T. Alright, and in order to solve for force, we divide both sides by delta T. So we will obtain an answer, an equation. Net force is equal to the impulse divided by time. And we can substitute all of the given. So we already solved for the magnitude of the impulse. That's 26,400 kilogram meters per second divided by 0.15 seconds. So the net force received by the car is 176,000 newtons. Or you can write it down using scientific notation. That's 1.76 times 10 raised to 5 Newton. And this is our final answers. Or these are our final answers. Alright, so again, if you had any questions or if you're still confused with the solution proper, you can still go back using the timestamps that I have indicated in the description box. Alright, so let's proceed with the next problem. So the next problem, I have here the choices, and you can pause the the video, in order to solve, or in order to have more time in solving these sample problem. So according to the problem, we had a 100 kilogram man and a 50 kilogram woman on ice skates standing facing each other. If the woman pushes the man backwards so that his final speed is 1 meters per second, at what speed does she recoil? So imagining or assuming that the ice skate is again frictionless. So this problem is in an isolated system, which means that the concept that we will be using is the conservation of momentum. Alright, so if you're done, the answer for this question is letter E. Alright, so letter E is the correct answer. So just look out, just look for the solution that we had already written in here. Alright, next, sample problem number 7. So sample problem number 7, a child bounces a 100-gram super ball on the sidewalk. The velocity of the super ball changes from 10 meters per second downward to 10 meters per second upward. If the contact time with the sidewalk is 0.1 seconds, what is the magnitude of the impulse imparted to the super ball? Since obviously the problem looks for impulse, so definitely this is a non-isolated system problem. That's why we use the impulse momentum theorem in order to solve for this problem. The first thing that you need to do is to convert this one into kilograms. So that is equal to 0.1 kilogram. And then just note that we had here different directions for velocity. So since the first one, or the first direction, or the first velocity that was mentioned in the problem was directed downwards, this is negative 10 meters per second. And the final velocity is upwards, that's why it's positive 10 meters per second. Alright, so the answer for question number 7 is letter B, 2 kilograms meters per second. Alright, now that we solved for the magnitude of the impulse, let's try to answer sample problem number 8, which actually wanted to know the magnitude of the force between the sidewalk and the super ball. So in order to do that, the equation that we derived earlier, that is the net force, is equal to the impulse divided by the time that it took for the collision to happen. Alright, so the answer is letter C. Alright, so yeah, this ends our discussion for momentum and impulse. So in the next video, we'll try to understand and integrate the things that we learned in our discussion of momentum and impulse within collisions, and the types of collisions that you may encounter as well in a real setting. Alright, so I hope that you learned something from this video, and see you on the next one.